The technical program for the 13th Electrical Electronics Installation Conference is now history. From among the many fine papers presented at this conference, we have selected the following paper which we feel will be of interest to you. The author of this paper is Thomas W. Dakin, who is the manager of electrical performance of insulating materials from the Westinghouse Research Laboratory, Westinghouse Electric Corporation. The title of his fine paper is Voltage Endurance of Cast and Molded Resins. May I present to you Thomas Dakin.
This paper is concerned with the delayed failures that occur in cast and molded resins as a result of partial discharges. These failures could occur in service if the resins are operated above the stress at which partial discharges would occur. In the first slide, I am showing here a curve which is schematic, indicating the decline in voltage breakdown as a function of the time of exposure to the AC voltage which is applied to the resin. This decline is due to partial discharges which can result in delayed failures. This curve shows a band of values which is representative of the distribution, the variability of the times to failure for a given specimen or type of specimen or a given resin material. This variability occurs in terms of a variation in voltage of breakdown at a given time, or a variation in time to failure at a given voltage stress. You will notice on the curve that the level tends to approach a threshold. This threshold is the threshold for the onset of partial discharges. The dashed line, horizontal line, is drawn to intercept the minimum level at which this may occur, because we believe that in cast systems in particular that there is a distribution of sizes of cavities and stress concentrations locally in the resin system. The operating voltage should be set for a long time life below this minimum threshold. If we plot actual data, as we have here, as a function of the voltage stress in volts per mil versus the logarithm of the failure time, we get data like this, which was obtained on a polyethylene terephthalate plastic film. You will notice here that there are two curves. One of the curves is plotted as was the schematic curve you just saw, as a function of the stress linearly and the time as a logarithmic function of the time. Another method of plotting such data as this is shown in the second curve, upper curve. This curve is plotted as a function of the logarithm of the voltage versus the logarithm of the time. The logarithmic stress curve or voltage curve is a scale is given on the right side of the graph. This curve has been used, or this method of plotting has been used more commonly by many investigators, but it has a doubtful theoretical or basic foundation. It does fit, as you see here, the data points over limited ranges of the time and voltage stress. We feel that this log-log type of plot, as shown schematically here in the upper of the two curves on this slide, is not as good a way of plotting the data as the curve below, where we have plotted first the breakdown time on a log scale as a function of the stress, and then we have also plotted another factor which is the product of the breakdown time and the difference between the threshold stress and ES and the actual applied stress. When we plot the data in this manner, we find that it is converted to a straight line, as shown in the upper of the two curves on the lower graph. The basis for this method of plotting, which is illustrated here again on the actual data which was shown in the second slide, is based on the fact that the quantity of discharges per unit time is the determining factor in the rate at which it approaches failure. We feel that the failure occurs when a sufficient number of discharges have been striking the surface of the resin. The quantity of discharges is indicated here by the product of a constant which we can say is due to the discharge density, in other words, the number of discharges per unit area, and the frequency. The number of discharges is nearly constant at each cycle, so that if we multiply the number of cycles per unit time, we get the number of discharges per unit time. And then we have added this other parameter here, the applied stress minus E0, which is the threshold stress for discharges. The derived relation then, using this quantity, is that the breakdown stress minus the threshold stress is equal to a constant times the log of this product of F, the frequency, times the E minus E0 quantity, which is the over voltage above the threshold voltage, and the time, plus another constant, which sets the level of the line. This line extrapolates to 0 at a stress equal to E0. We feel that below this stress, no failures should occur due to the partial discharges. Here we are representing some recent data showing the effect of partial discharges measured with cavities placed between two films. The dashed line is data that was recently published last year from a group of laboratories in Japan. This data, which was obtained using 3 plastic films with a hole between the center film in which the discharges occurred, tends to overlap older data which we had published from the Westinghouse laboratory some years ago, using, instead of the 3 films, we used a mica sheet which was resistant to the discharges to protect the surface from the edge discharges at the upper electrode. You can see that the 2 lines, straight lines here, the 2 straight solid lines, show that the times to failure are longer when we have internal discharges than with surface discharges, somewhat longer. There are a number of factors which influence this difference between internal discharges and surface discharges. The internal discharges will start at a higher voltage because the breakdown voltage of a cavity, such as is represented here by the sketch in this slide, is smaller than the breakdown spacing that would be prevalent at the edge of the electrode on the surface. Another factor which influences the breakdown time in cavities is the stress concentration. We show here the data obtained on the stress distribution with 2 different shapes of cavities. The lower curve in this slide shows the stress distribution, the electric stress distribution, as a function of the distance from the center of the electrode to the edge of the cavity. This stress rises to a high value of the order of 10-fold above the average stress in this type of arrangement. In this case, tests were made to failure. The discharges occurred in the space between the pin inserted into the cavity, the metal pin, and the bottom of the cavity. Because of the stress concentration at the corner edge of the cavity, which is the bottom of a cylindrical space, is very high, and this influences the breakdown to occur at that point. A treeing-like breakdown pattern developed, and failure occurred from the edge of this cavity. This has led us to believe that the shape of the cavity is extremely important in the resistance or the failure of discharges in such cavities. The upper figure in this slide shows the stress distribution of a cavity formed by a hemispherically ended cylindrical hole into which a pin was also placed to form the upper electrode. You can see that the maximum stress, which here occurs at this center bottom of the cavity, is less than it is in the lower case. It's 6 versus 10 in the lower case. This produced a longer failure time than in the lower case, as shown in the next slide. You will notice that a stress of the order of 88 kilovolts per millimeter. At the left, we have the breakdown data obtained for a cylindrical cavity with a square edge bottom, as shown in the previous slide. To the right, we show a band of data at the 8 kV per millimeter stress, which represents the failure times at the bottom of the cylindrical cavity having the hemispherical end, which had the lower stress. You will notice in particular that the failure time with the sharp-edged cavity is much shorter even than with the cavity formed by a hole through a sheet of mica, which is represented by the straight slanting line. This is the same data that was presented in a previous slide. This very short failure time was one of the reasons why we suspected that the stress in the resin at the bottom of the cavity was a very important factor in the failure under these conditions. The data for these two different cavities, the cylindrical sharp-edged cavity and the hemispherically ended cavity, were both increased by the factor of the stress concentration. The 8 kV per millimeter value was the average stress. The spacing of from the bottom of the cavity in each case to the lower electrode. When we multiply the average stress by the stress concentration factor as obtained by the stress distribution plot from the previous slide, we find that the values come up and tend to form a band of data which is more comparable and somewhat above the values obtained with the cavity through the mica, the hole in the mica. We feel that we have now shown that the breakdown times with internal discharges in cavities is a function of the stress concentration in the resin, and also a function of the log of the breakdown time is on a log scale is a function of the stress linearly. We are showing on this curve comparative data on a variety of different systems. The line for the polyethylene tyrothalate, the mylar, is reproduced here, together with the data recently published on cavities in films published in Japan, and the data for a new set of tests which were started recently, several years ago, and which are still continuing on cast epoxy resins, first with a silver paint electrode using a specimen which had a recess, deep recess in it. We found unexpectedly that the silver paint electrode was not a sufficiently good contact to the resin, that in applying the paint, cavities, tiny micro cavities were produced under the paint, and this caused a delayed failure, even though in this case we could not usually measure any discharges above 0.01 picocoulombs, a very low level, the detection threshold limit for our most sensitive pulse detection equipment. We have previously shown that when the area of a small cavity is sufficiently small, that the discharge magnitude, which is proportional to this area, will correspondingly be small. Therefore, very small microcavities can occur which are undetectable by the present pulse detection techniques. Nevertheless, in spite of the fact that no discharges could be measured in such specimens, delayed failures did occur, showing a trend with time, much as is seen in other cases where we knew that discharges were occurring, either on the surface or in artificial cavities. When castings were made in such a way that electrodes were cast into a resin under vacuum and with electrodes prepared so as to obtain maximum adhesion of the resin to the electrodes, the level of the breakdown stress at a given time shifted upward by a factor of more than 2. This is represented by the line upward, the upper line in this figure, and the band of values extend above the stress level shown on this curve. Nevertheless, even in this type of specimen, where we have done everything we know best to do to avoid discharges, we still get delayed failures, possibly due to separation of the resin at some very small areas on the surface of the electrode. We have plotted here on the same graph for comparison the volt time curve for mica generator insulation, which is the lowest curve on the line. It has the least slope. We believe that the slope of these lines is a function of the resistance of the material to the discharges, that the level of the data, the lines, is dependent upon the stress concentration and defects that occur in the specimens. This conclusion is consistent with the most of the data of this type that we have obtained so far. For example, the cast epoxy, which here has a filler, silica filler, is more resistant than a clear resin to discharges. But because the filler increases the stress in the resin somewhat, the breakdown voltage at short times is lower, and the level of the curve is down. You can note it was noticed here and is noticed here that the specimens of cast epoxy, where the electrodes were cast in under vacuum, have higher level, but pretty nearly the same slope of the volt time curve as do the specimens with the silver paint electrodes, where we believe that cavities occurred underneath the paint. In conclusion, I would like to point out that in most of the cases where we have measured discharges, we get similar results to where we have large cavities with measured discharges. But that when we make these cavities very small so as to raise the threshold voltage, that this produces longer failure times and better resistance, better long-time voltage endurance. We do not believe that there is a great deal of difference between the failure times with and without the cavities, unless the discharges are not continuous, or as sometimes has been observed in internal sealed cavities. We have shown here in this data that the stress concentration at the cavities is in the resin, and next to the cavities, is a most important factor in determining the failure time, because it is the actual stress where the discharges are occurring that influences the level of voltage for failure at a particular time. This still remains to be a puzzling, somewhat puzzling problem, which needs to be clarified further, and tests are continuing over very long times on silica-filled epoxies where the electrodes are cast in. Thank you.